like 1 year. But they, of course, now you can use the basement. Yeah.
Right, because he was the physics guy.
Yeah.
Okay, let's test.
The rock room. But it's where all the oh yeah.
Hello, hello, hello. Okay, so I'm using, I want to use that. Dan, can you hear me?
Yep.
Good, okay. All right, we're gonna go ahead and get started. I have a handout. I guess I can email you the handout. Let me do that.
Okay.
Yeah, yeah. Okay, check your email, see if you got it.
Yep, I got it.
You got it, excellent, okay. We'll go ahead and get started then. Okay. Yeah. Sometimes called skin tags,
Yeah, so.
but on diabetics, they tend to be flat instead of sticking out.
My mom's blood.
Yeah.
Awful. I tried really hard to get rid of them, but it really
Well, skin emollients are quite important, but they're special emollients made for diabetics. Okay, we're going to talk about how you move cholesterol through the body. This turns out to be very highly regulated and biochemically fascinating. So let's get started. Lovely day today. Hope you guys had a chance to enjoy the nice weather we had. And it was great. It was really great. Good. Well, work is good. Let's pray. Father, thank you for this nice day. Thank you for a ground that's not obscured by snow anymore. Thank you for warmer temperatures. Thank you for the chance to go outside without thick coats on. Thank you, Lord, for watching over us. We pray for Dane and his wife that they'd be able to stay well or get well and then stay that way. Watch over them, please. And thank you, Dane. Gets to come back to us, hopefully in a timely fashion. In Jesus' name, amen. How is your missus, Dane?
She's good, actually. She's been symptom-free for about a week, a little over a week now. She's been back at work for the last 4 or 5 days.
So she had a very mild case.
Yeah, and she got the Lilly transfusion.
Oh, okay.
Yeah, she got that like 2 or 3 Fridays ago. So yeah.
For those of you who don't know, that's the Lilly product is a combination of 2 monoclonal antibodies that bind to the spike protein and prevent it from causing infection. And it's very effective. If you have a high viral load, it can knock that load down and help you clear the virus from the system. It's very effective. No, it's specific for COVID-19. Now, there are new strains that will not be cleared as easily by this cocktail. So the South African strain, the B1351, and the Brazilian P1 strain is not as easily cleared by these.
I should probably give you a heads up. I get my second Thursday evening, so I
just let me know how it goes. Just let me know.
Yeah, this stuff was supposed to be long. Right. I like called my work. I was like, can you not have me work that day?
We'll see. We'll see. Okay.
Hopefully I'm fine.
Cholesterol is very insoluble. You simply cannot throw cholesterol into the bloodstream and expect it to go where you want it to go, because at the concentrations at which you want to deliver it, it will precipitate out. In fact, it will crystallize out. Cholesterol crystals are sharp little needles. They cause a lot of damage. And so just secreting them into the bloodstream is a bad idea. So what do you do to transport them? Answer is you put them in a taxi. Now this taxi is called a plasma lipoprotein. And there's several different types of plasma lipoproteins. They have different functions. So the structure of these is shown here, and these will help you transport cholesterol, and they will help you transfer triacylglycerols as well. So fat and cholesterol is effectively transported by these plasma lipoprotein particles. So look at the structure of this. This is common to the structure of all plasma lipoproteins. You have an outer phospholipid monolayer. You don't have a bilayer, just a phospholipid monolayer. Inserted into this monolayer are free cholesterol molecules. The amount of free cholesterol in these plasma lipoprotein particles is not that significant, but it is in this monolayer. Also inserted into the monolayer are a group of very interesting proteins called apolipoproteins. These people do to all the chalk. Now, apolipoproteins structurally have to be able to fold such that one side can properly associate with this very hydrophobic interior. The outside, however, has to be able to associate very effectively with the aqueous exterior. So these proteins are two-toned, if you will. One side is very hydrophobic. The other is very hydrophilic. And that folding allows them to associate in the membrane and jut into the interior of this apolipoprotein particle. Inside,
The slides aren't moving for me.
slides aren't moving.
Uh-uh.
Okay, we'll try it again.
Okay, that's fine. Thank you.
No, hydro. Okay. That move?
Yep.
Okay. Then that move?
Yep.
Okay, good. All right.
Thank you.
Okay. So inside you have the little things that look like E's. Those are meant to be triacylglycerols. So these will carry triacylglycerol molecules, fats. Then these things here that look like sausages, those are cholesterol that's been acetylated. It's been esterified. So these are cholesterol esters because they have an ester bond to an acyl group. They're loaded into the lipoprotein particle by virtue of the fact that they're attached to the acyl group. So We talked last time about that enzyme called ACAT, acyl cholesterol acyltransferase. It takes cholesterol and this acyl-CoA is usually a palmitic acid, but it can be a unsaturated fatty acid too, but it's usually a palmitic acid. And then you, by virtue of ACAT, you're going to, coenzyme A will be the leaving group, and you'll now have a cholesterol ester. Cholesterol, so it'll be cholesteryl palmitate, cholesteryl myristate, cholesteryl stearate, cholesteryl oleate, cholesteryl, you know, whatever. So that's what these are, these things that look like Eureka's cowpo, which is a sea cucumber. Now, there's different types of these plasma lipoproteins. They have different compositions in terms of their percentage of cholesterol esters versus their percentage of triglycerols, and also the types of apolipoproteins on their surfaces will also be different. Depending on the type of plasma lipoprotein will determine its function. So as we said, your apolipoproteins will have this common structure where you have amphipathic helices, and these helices will, on one side, be hydrophobic, on the other turn, be hydrophilic. Therefore, you'll have turns where the hydrophobic amino member, a turn of an alpha helix about every fourth amino acid, ends up being on the same side. So you have every fourth amino acid has the same chemical characteristic. Every fourth will be hydrophobic, every fourth will be hydrophilic, something like that. And then they'll make a face of the protein, one of which interfaces with the interior of the apolipoprotein particle, the other of which is on the surface and is associated with the aqueous blood. And so here is some structural work that's been done on a couple of these apolipoproteins. So here's ApoE. It's a series of these helices. These helices are very hydrophobic on one side, very hydrophilic on the other. Here's ApoA1. Looks a little bit like a bear trap here, but this area that sits underneath here is all very hydrophobic. If you look at it kind of just on the top here, this bottom is very hydrophobic. And then if you swing around and look at it this way, it looks a bit like an infinity sign. And then if you turn it and look at it straight on its side, it looks like that. And the one side sits in the apolipoprotein particle, the other interacts with the blood. And you can see these are helices. And so these helices, this face will be hydrophobic. The bottom of that face will be hydrophilic. You see this over and over and over and over and over again in apolipoproteins. All right, now to consult the handout, you look at page 2 of the handout, you can see that each lipoprotein particle is classified according to its density. Its density. So here is the hydrated density for each one of these in grams per milliliter. So your least dense particle is a chylomicron, a chylomicron. The second is the very low density lipoprotein particle. Then you have the low density lipoprotein particle. There's a particle that's kind of straddles these two, and that's called an intermediate density lipoprotein particle, or IDL. It's kind of in between the VLDL, the IDL, and you have a high density lipoprotein particle, HDL2, HDL3, and then another particle that is very dense, just called lipoprotein A. Lipoprotein A.
Isn't it LDL that they kind of measure?
That's the one that's a supposed bad cholesterol, which I told you I don't like that term, but it works, I think, for medicine. In terms of biochemistry, it sounds to me like you're scolding it. And we don't scold molecules in biochemistry, we study them. Also, it's only bad if there's too much of it. Then it's bad. It's also only bad if it gets oxidized. Then it's bad, as we'll see. So that's why I don't like the term bad cholesterol, but the name is stuck, so there you are. Okay, here are some of these particles in the electron microscope. This comes from your book. You can see the chylomicrons are big, and they're very particle-y looking. They're not very dense. These are made by the small intestine. So they're not made by the liver. Virtually all the other particles are made by the liver. This is not. This will take dietary fat and cholesterol to the liver. To the liver. So that's a chylomicron. That's the least dense of the particles. Then you have the VLDLs, smaller than the chylomicrons. LDL, which are even smaller and denser than the VLDLs, than the HDLs, which are even smaller and even denser than any of these other particles. Now, if you look also at page 2, you can see that the various apolipoproteins that each of these contains are also different. Now let's take a look on page 1 for the function and the properties of these different apolipoproteins. So first, there are the class A apolipoproteins. So there's A1, A2, A4. You can tell the biochemist name these. They're not very interesting when it comes to theirs. Sorry? A3 turned out to be an artifact. Then the Bs. Bs are labeled according to their molecular weight. So there's a B100, which is 100 kilodaltons in size. Then there's a B, ApoB48. ApoB48. Now, ApoB48 is specific to chylomicrons. Is specific to chylomicrons. ApoB100 is found on the surfaces of LDLs and VLDLs. LDLs and VLDLs. Then you have the ApoC class, C1, C2, C3, and C 2, and 3 are going to be very important because they are going to activate something called lipoprotein lipase. Lipoprotein lipase is going to cause these particles to leak fatty acids. And they're going to deplete these particles of fat. Why is that important? It's important because several tissues use fatty acids as their preferred energy source. Why do they do this? Well, one, fatty acids are a very good energy source, as we saw when we looked at beta oxidation. 2, by using fatty acids, they spare glucose for the brain. And their source of fat comes from these lipoprotein particles. So tissues like skeletal muscle, tissues like the kidney, tissues like cardiac muscle, tissues like adipocytes, tissues like the thyroid, so on and so forth. These types of tissues will preferentially use fatty acids. ApoD is specific to HDL, as is ApoA1 and ApoA2. And then there is ApoE. ApoE is incredibly important because ApoE allows particles to be taken up by the liver very quickly. Very quickly. Because of the ApoE receptor that's found on liver cells and other cells too. Okay, then if we turn the page, look at the table, we can see some of the different apoproteins sported by these various particles. Okay, let's go ahead and get started with the different particles. Chylomicrons. When you eat dietary fat or dietary cholesterol, so let's say that the two of you have pancakes with whipped cream for breakfast. No, waffles with whipped cream for breakfast. Belgian waffles with whipped cream for breakfast. Okay. Cream contains fat. The fat will be broken down by pancreatic lipases in conjunction with bile salts that will emulsify the fats. The fats will be the fatty acids will be taken up by enterocytes in the small intestine. In those cells, they'll be resynthesized back into fats. They'll be resynthesized back into fats, particularly if they're long-chain fatty acids. If they're short-chain fatty acids, they'll usually just go straight through into the bloodstream. That'll be picked up by albumin, not a problem. Long-chain, though, will get remade into fats. Then the cholesterol, also from cream. That will be taken up by a cholesterol transporter, the NPCL1 transporter. That cholesterol will be esterified to a cholesterol ester by ACAP. The cholesterol ester with the fat gets packaged into a chylomicron. The chylomicron is then excreted by the enterocyte, but it's too big to go into the bloodstream. Instead, it goes into the lymph. It goes into the lymph. Now, from the lymph, it will sojourn through the tissues. As it sojourns through the tissues, it will encounter endothelial cells Pretend that's your chylomicron. And it's going to acquire in its circulation ApoC proteins and also ApoE. It will acquire those from plasma HDL. So two of these will be ApoC2 and C3. Like that. These cells are going to have any more colors? Are going to have this lipoprotein lipase protein on their surface. When LPL is bound by ApoC2C3, it's activated. It's now going to degrade the triacylglycerols in here. And this is going to leak fatty acids. Those fatty acids will be taken up by these cells and they will go to the tissues and it'll feed them. So as the chylomicron circulates through the lymph and then eventually through the blood, it's going to be depleted of fat. So essentially by going into the lymph, it takes the long way, the scenic route, to get to the liver, but that's good because as it circulates, it can feed these various other cells that are fed by lymph and capillary beds. And the chylomicron will be able to give them fatty acids from its store of fats. All right. Is that clear so far? And again, the lipoprotein lipase does not degrade the chylomicron, simply causes it to leak fatty acids. It leaks them to the nearby tissues. And it's bound to the luminal surface of endothelial cells. It's bound to heparan sulfate, which is an external glycosaminoglycan. So here essentially is the role of your lipoprotein lipase. You have your chylomicron, the endothelial cell with its lipoprotein lipase. The chylomicron will release triacylglycerols, and eventually it will get to the liver, and it's so depleted of fat, it's now called a chylomicron remnant. Chylomicron remnant. Now the chylomicron also has acquired another apolipoprotein called ApoE. The liver has a high affinity ApoE receptor. In fact, it has a couple of them. There's several proteins on the surfaces of hepatocytes that will bind ApoE very tightly. So it can take up chylomicrons like that. So chylomicrons, once they get into circulation, they will be taken up by the liver pretty quickly. So these don't contribute to atherosclerosis directly. Now, what does the liver do with all that fat and cholesterol? Here's what happens next. All right, so the C2, ApoC2 activates LTL, chylomicron remnants return to the liver. They're the least dense. They contain ApoB48. They're the only particle that contains ApoB48. They acquire ApoE, ApoC2 from HDL, and ApoC2 and C3 activate LPL. ApoE causes the liver to take them up very efficiently, and ApoB48 is a marker essentially for chylomicron. And I said that already. Okay, moving here. And then the ApoE receptor then gets moved and can then the hepatocyte will fuse that endosome with a lysosome, and it will liberate the contents of the chylomicron. So you get from that cholesterol and triglycerols. The hepatocyte will then use the fat, the cholesterol to make a VLDL, a different plasma lipoprotein particle. Here's the reason why. Chylomicron is very good at delivering fats. It's not as good at delivering cholesterol. Most tissues can make their own cholesterol. Some tissues, however, need more cholesterol. So for example, tissues that make steroid hormones. Those steroid hormones are made from cholesterol. Skin also requires more than the average amount of cholesterol because skin is replaced very quickly. Outer levels of the skin also don't have a good blood supply. And so you need to deliver cholesterol also to the skin. So VLDLs, very low density lipoprotein particles, will export the cholesterol and the fat to extrahepatic tissues. So the fat for VLDLs comes from fat that might have been released from adipose tissue, fatty acids that are circulating in the blood directly down to albumin that get delivered to the liver, also from carbohydrates that get converted into fatty acids in the liver. So back in the 90s, there was a big push to remove fat from the diet. And what we've replaced that with now are diets that are high in sugars, particularly high in fructose corn syrup. We didn't count on the fact that you can take sugar and you can make fat, and sugar will jack up your LDL actually better in some cases than fat will. So some of these low-fat diets actually are very bad for you because they essentially replace those calories with carbohydrates, and those carbohydrates can actually be just as deleterious to your cardiovascular health than the fats themselves. And so now you're seeing diets that are trying to attempt to correct that. My beef has always been just eat a bloody balanced diet and forget the fad diets.
You could have it stripped and do it out of the way.
Well, so for example, the Atkins diet. The Atkins diet, you lose a lot of weight at first because you cut out carbs. Carbs are hydrated. A lot of that early weight you lose is water. So people lose all this weight in the first couple of weeks, and then they say, see, it works. Now, some people, like the South Beach diet, find that the glycemic index concept helps them manage sugar intake. You should get about 30% of your calories from fats. You should get 20 to 30 from sugars, and then about 30, 35 or so from protein. Yeah, yeah. So balanced diet is just very important. And complex non-digestible carbs are also important because it's clear Americans also don't get nearly enough fiber. Let's see, RDA says anywhere from 10 to 12 grams of fiber a day. Most Americans get maybe 6. Well, both soluble and insoluble fiber. You need a combo of both. And Americans pretty clearly don't get enough of both. So anyway. All right, so you can also get them from the hydrolysis of triglycerols on capillary endothelia in the liver itself. So the VLDL, of course, will contain phospholipids, free cholesterol in that monolayer. Then they'll have cholesterol esters and triglycerides. And if you look at your handout, you'll see they contain essentially VLDLs, 14% by weight phospholipids, 4% by weight free cholesterol, 16% by weight cholesterol esters, 90% triglycerol, whereas your chylomicrons were mostly triglycerol. So these have more cholesterol in them. They also have apolipoproteins, C100, C2, C1, C2, C3, and ApoE. C1, 2, and 3, ApoE and B100. ApoB48 and ApoB100 are made from the same gene. The difference in your adipocytes, in your hepatocytes and your liver is that the RNA in the liver is edited. You have editing of the RNA. That editing removes a stop codon. So in the enterocyte, you make the RNA, the protein's translated, it stops at codon 49 because that's a stop codon. In the liver, codon 49 is modified by an enzyme called adenine deaminase. And you convert that stop codon now into a coding codon, and you translate it so that you now have 100 kilodalton protein, not a 48 kilodalton protein. All right, so the VLDLs are released from the liver into the blood. They are transported through the blood to muscles, to adipose tissue, to anywhere the blood goes. So the delivery of fats to adipose tissue, that occurs via VLDLs. And then your lipoprotein lipase will also take up fat via ApoC2 activation. You may have heard this statement, if you have more muscle, you burn more fat. That's actually true because resting muscle preferentially uses fatty acids as their energy source. They get that fat from the VLDLs, so there's less VLDL fat delivery to adipocytes. That's why when you lose weight, you want to lose weight, you shouldn't just do cardio, you should do some lifting as well. The VLDL will be depleted of fat. It will then start to increase in percentage of cholesterol esters by weight. Here's a picture from your book showing the output of the liver after a fat-rich meal. Here is a fasting serum. You can see right through it. You put your finger through there, you see your fingernail. If there's a cut on your finger, you'd see it. You wouldn't see it from this. That's due to VLDL in the plasma. This is the reason why when you go to the doctor for a lipid panel for physical, he or she wants a fasting lipid, not a eating one because the amount you put out after you eat depends on what you've eaten and also depends on your genetics. To see actually what actually your baseline is, has to be a 12-hour fast.
Yeah, mine was 5 because right as the 12 hours almost.
And it's surprising how that'll do it. Just what you eat right before.
I was like, well, I ate McDonald's and then I got
Yeah. I came back from vacation and my sister-in-law, she doesn't cook very healthy. And I came back and my cholesterol was really high. And because I'd spent vacation with Aunt Gwen, basically, in her cooking. She cooks for farmers. So they work hard. Anyway, so this shows you essentially what you get after you eat like that. Now, turns out high carb meals will cause a sustained elevation in plasma VLDL, not just a high bump, essentially. So VLDLs after a high cholesterol diet will contain far more cholesterol esters because you're using the acetyl-coenzyme A from sugar breakdown to make cholesterol. Okay, so while the VLDLs are circulating, yes, they're depleted of fat, but they also undergo surface modification because they're interacting with other plasma lipoprotein particles. So they will acquire ApoC and E from HDL particles. Remember, your VLDLs contain ApoB100. They're also being depleted of fat. And it's clear that macrophages can also take up cholesterol, and they have a specific beta VLDL receptor for taking up VLDLs and removing them from the circulation. This is one of the reasons why tissue that's being repaired can often really suck up a lot of resources, including VLDL. Now, if the VLDL is depleted of fat, and if in its interactions with other particles, it loses ApoC proteins. So now it just has ApoB100 and ApoE. It's now an intermediate density lipoprotein particle, or an IDL. If you look at the table on your handout, you'll see the IDL has ApoB100 and ApoE, and it has twice the levels by percentage mass of cholesterol ester. It's a smaller particle, and it is more dense than the VLDL. Now, because it has ApoE, it is easily removed from the circulation by the liver. So this particle is not typically of great import when it comes to atherosclerosis. IDL can still deliver fats to other tissues via these other mechanisms, but you can't do it via LPL. You have to have a receptor directly for LDL, which some tissues have. So the kidney has one, endothelial cells, some endothelial cells have one, other cells have one. If the particle loses ApoE, it now gets transformed from an IDL to a LDL, a low density lipoprotein particle. This particle, as you can see on your handout, is 42% cholesterol esters by mass and 7% triacylglycerol. So this is a particle that is essentially is more or less just cholesterol. Just cholesterol. Also, in order to remove this particle, you must have the LDL receptor. Only a few cells have the LDL receptor. Furthermore, uptake of particles by the LDL receptor is highly regulated. So it's measured, it's gradual. You remove the receptor from the surface, you then have to recycle it. Then you take it up, you have to recycle it. So this is a process that takes a while. Consequently, LDL particles can have a residence time in the bloodstream of several hours to 2.5 days. That's why this particle is the one that's significant when it comes to atherosclerosis, because it just has ApoB100. It's only taken up by the LDL receptor, which only a few cell types have, and its uptake is very slow.
You only make LDL from IDL?
Yeah, from VLDL ideal, yeah. And the pathway that I'm detailing is meant to be diagrammed down here. That's what that's meant to be. Probably looks a little cryptic, but that's what it's intending to do. Show you essentially how you go from one to the other to the other. All right, here is the means by which you take up the LDL particle by means of the LDL receptor. Now, fortunately, the process has been very heavily studied, and Brown and Goldstein won the Nobel Prize essentially for their work that showed the uptake of cholesterol and the cholesterol receptor, well, the LDL receptor, and so on and so forth, and blah, 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 and all that. Oh, there we are. When you take up this particle, it gets put into an endosome. That endosome then is going to recycle the LDL receptor. The rate at which the LDL receptor is recycled turns out to be subject to immense genetic variation. Also, the affinity of the LDL receptor for ApoB100 is subject to genetic variation. And then this particle will fuse with a lysosome. In a lysosome, you have an acid esterase, that cleaves the cholesterol esters. You now have free cholesterol that's delivered to the ER. And now this will inhibit endogenous cholesterol biosynthesis. It will also increase the gene expression of the LDL receptor. That's actually what that will, excuse me, it will actually decrease the expression of the LDL receptor. So consequently, the more cholesterol you bring in, the slower you're going to clear those particles. So if you can see, you keep eating high-fat diets, that particle now is going to build up in your bloodstream. Now, there is a peptide that has come to the attention of researchers in the past, 10 years or so. This peptide is secreted by hepatocytes, and it is called the pre-convertase phytolysin kexin-like protein number 9, which is mercifully abbreviated PCSK9. What does this do? This protein, if it binds the LDL receptor, will target the LDL receptor for the lysosome where it's degraded. So this is meant to be a regulator of the number of LDL receptors you have on the surface of the cell. And now there are therapies that consist of monoclonal antibodies against PCSK9 that increase the half-life of the LDL receptor and the number of LDL receptors on the surface of hepatocytes and thereby increase clearance of LDL particles. And these, evocolumab is one, and alirumab and things like that. These are monoclonal. Let's see what the Repatha is one, and Evocala, is that right? I think is the other. These are products that you can use for people with genetically high levels of serum cholesterol. They're not going to be used in people whose cholesterol levels can be controlled by other means. Very good. Okay, so you have essentially this control on whether or not the LDL receptor gets recycled, PCSK9. If PCSK9 is bound to it, it doesn't get recycled. PCSK9 is not bound to it, it gets recycled. So that's a control on numbers of these particles, excuse me, the receptors on the surface. And here we have this therapy with these monoclonal antibodies to PCSK9 that bind PCSK9 and they allow LDL receptor recycling and prevent its degradation. All right, let's talk a bit. Well, first, let's, yeah. So that's what's on your handout, essentially showing you, essentially, we go from the liver, we could say intestine, chylomicron, sojourn through to the liver. Liver makes VLDL. VLDL acquires ApoE, ApoC from HDL. LPL then is activated by the ApoC proteins. This will then leak fatty acids that then loses ApoCs and becomes an IDL. It loses then ApoE, then becomes an LDL. The LDL then can be retaken up by the liver, by the LDL receptor, or by other tissues that have the LDL receptor, like scavenger cells and then other extrahepatic tissues. So for example, adrenal gland cells have LDL receptors. They can take it up. So does gonad cells. So the estrogen synthesizing cells of the ovary, they can take up LDL. And so on and so forth. And then so can macrophages, which we will see in just a bit. Let me stop and see if there are questions. This is a bit of a long pathway, but makes sense, I think. There's a logic to it. I hope you can see the logic to it. Okay. Jenna, what does lipoprotein lipase do? Yeah, yeah, and VLDL as well, not just chylomicrons. And Amanda, ApoB48 is found on what? Yeah, good. And Dane, ApoE, what's ApoE good for? What's it used for?
I know
ApoE.
binds to specific receptors. I wrote it down somewhere.
Yeah. Binds to receptors, you got that right. Receptors that are found in what cells?
Both of the LDLs.
Right, VLDL, IDL, chylomicron remnants, and it's found on what cells?
Like in terms of part of the body.
Yeah,
Um,
that's actually important. Okay, write this down. Liver cells.
liver. Okay, I was gonna say
Liver cells.
endothelial or
Liver cells. Liver cells clear the chylomicrons, the IDL, the VLDL from circulation.
okay.
Liver is going to clear chylomicron remnants, VLDL that doesn't get converted to IDL or LDL. It'll clear that. It'll also clear IDL via the ApoE receptor.
Okay.
Like I said, there's several proteins that bind ApoE. So there's lots of receptors that can bind those particles and remove them from circulation. Therefore, they're removed from circulation very efficiently.
So ApoE is on.
Chylomicrons, IDLs, VLDLs, and it tends to acquire them from circulating HDL. So let's take a look now at the LDL receptor. LRP, LDL receptor protein. So this is encoded by a 40 kilobase long gene that contains 18 different axons. It contains a single membrane spanning domain that is 22 amino acids long. It has a signal sequence, so it is trafficked to the ER when it's made. It also has domains that show a good deal of homology to several other proteins, including epidermal growth factor precursor right there in the middle. There's also complement protein C9 homology that I believe is up here. And then it shows similarity to several clotting and anti-clotting proteins as well. Here is the structure of the protein. So the ligand binding piece is found in the amino terminus. The epidermal growth factor piece is here after the ligand binding piece. Then you have a piece towards the transmembrane domain. This piece is very highly decorated with sugars. This piece here, by the way, will play a really important role in the lysosome in letting go, because the high acidity in the lysosome will cause this to change structure. And then you have a cytoplasmic tail that's not terribly long, but that tail is important. It's 50 amino acids long. Yeah, we are. We're out of time. We're out of time. Okay. We will pick this up on Wednesday. And let's see, Dane, it's 2 weeks from the 1st of March, right?
Thursday should be my last day.
Thursday should be your last day. Praise the
Yeah.
Lord. Okay.
Yeah,
You'll be back Friday then, but not
should
Thursday.
be. Yes, I should be.
Okay. We will look forward to it.
Yep, I am too. Trust me.
Um, We went down and saw my daughter
Mhm.
in Indianapolis. We went to dinner with them afterwards. We were talking with some people on her team. Those girls, one of them actually had COVID.
Mhm.
The others have been quarantined 2 times, 3 times, 4 times. They've had to go of it.
Yeah.
Just had to go of it. So,
Where does she go?
Greenville.
Okay.
Greenville. The girls' tennis coach is really cool. He's a
Mhm.
really cool guy. His daughter's on the team. She's just as nice as they come.
Yeah.
He's in good hands there.
Yeah.
They're good people. So,
That's good.
yeah. All right. I will see you on Wednesday.
Yep. See ya. Bye. Thank
Stay
you.
well.